Welcome back. Today we're going to talk about mass spectrometry. And here on the intro slide you can see a series of instruments, all of them being mass spectrometers of various sizes, different shapes, different designs, but they all accomplish the same task, which is to measure the mass of a molecule. And the way this is done via mass spectrometry is by ionizing a molecule. If you take an atom, molecule, and this could be a small molecule, big molecule, it could be an entire DNA sequence, a protein, as long as you remove at least one electron to produce a positive charge, you can actually use electrostatics and magnetism to determine the mass of the molecule as a whole. And the beauty of this process is that the mass of the electron is very much insignificant compared to the mass of an element, and even less when compared to the mass of an entire molecule. So we kind of go based on that premise alone. And the machine ultimately what it analyzes is the mass to charge ratio of the ionized particle. Now the way this is generally done is depicted in this diagram right here. So pretty much you inject your sample that contains the molecule that you're analyzing into the instrument, and the instrument has a compartment that is partly evacuated, and so you have a little bit of dispersal of your sample as the material kind of enters the compartment right here. But then there is this other inlet that lets you into another compartment that is held at an even higher vacuum. And when your substance enters this second compartment, it is met with what we call an electron gun. This electron gun, simply put, is shooting electrons perpendicularly to the direction of your molecules as they enter the second chamber. Now the collisions are elastic collisions that provide a certain amount of kinetic energy, and that energy is ultimately what is provided to ionize the molecules, thus yielding the positively charged molecule. Now here's where voltaic plates are utilized. So you have negative potentials that attract the positive charges of the molecules of the ions that you've generated. And so you have an acceleration towards the voltaic plate, but here is a bit of an opening, a slit, through which some of the material can go through. And then you reach the discriminator portion of the instrument. This is where different instruments have different setups. Right here I'm showing the quadrupole setup, which as the name implies is 4 poles. Two of them are connected to AC potential, whereas the other two are connected to DC potential. And by altering the voltage of the AC poles, you can actually make it such that this ion starts spinning and spinning and spinning. And if the voltage of these poles is set up to a specific value, which can very accurately and precisely be given by each one of the poles with the instrument, you can actually match it to a very specific mass that has to be present for a plus charge to actually go in a linear fashion from the beginning of this chamber all the way to the detector. If the mass is not exactly what's needed for this to kind of go in a straight line as it's going in the circles, what will happen is that the mass will just deviate towards one of the poles, collide with the poles, and lose its charge, and then no longer even reach the detector. So this is how you can separate the different molecules. And once you reach the detector usually is a metal surface that can easily lose electrons. And so when this particular cation reaches the detector, it basically collides against it. It's a big collision, and that collision has kinetic energy that is given to the detector and utilized to produce um, electrons. Pretty much, electrons come off the detector, which then are accelerated towards these voltaic plates of positive potential, and that collision creates more electrons that move over to this other voltaic plate of an even higher positive potential. So you end up with this cascade event of amplification to the point where a single cation hitting the detector can be amplified to a million, maybe even billions of times. So you need very little concentrations in order to detect samples. And this is one of the beauties and the power of mass spectrometry. Now, as you may recall from inorganic chemistry, elements are actually composed of a number of isotopes. And so when you look at the periodic table, and if we focus specifically on hydrogen and this subset of the p block of the periodic table, what you will find out is that there's a lot of natural isotopes present in many of those elements. Now here what I'm showing you is the Lockheed-Martin nuclide and isotopes chart, which is very much complete with all the different isotopes, both natural and artificially made in nuclear reactors, as well as all the different information that you want to know in terms of what kind of reactivity some of these isotopes may have, how stable they are, how unstable they may be, etc., etc. All right, so let's kind of start easy here. So since this is organic chemistry, carbon is going to be one of the central elements we're going to be thinking about. And the atomic mass of carbon is 12.011 grams per mole. And that's the value you get by looking at the periodic table. But the truth of the matter is that elemental carbon is made up of two main isotopes, carbon-12 and carbon-13. If you want to be technical, a tiny, tiny, tiny amount of carbon-14, which happens to be radioactive. But these are the main two carbon isotopes. Carbon-12 being the predominant one, 98.9%, and 1.1% carbon-13. So pretty much the atomic mass of carbon is nothing more than the isotopic mass of carbon-12 times its abundance divided by 100 plus the isotopic mass of carbon-13 times its abundance divided by 100, which ultimately gives you the 12.011 grams per mole, which you see in the periodic table. All right, now expanding on the p block and even including hydrogen in the picture, what I'm showing right here is all the various natural isotopes that all of these elements possess. And you'll notice that there's a few elements like hydrogen, fluorine, phosphorus, aluminum, arsenic, iodine that practically speaking only have one predominant isotope present in an elemental batch. The amount of deuterium is actually pretty small that is really not all that consequential. That being said, if you have a lot of hydrogen content like you do in the oceans, you can actually get some deuterium out of that water, right? But it's a very small amount. Now there's other elements that do possess two main isotopes like boron, carbon, nitrogen, and I'll even include oxygen here because oxygen 17 is very low in value, much like deuterium. And the abundances are, at least for boron, are 20% to 80%. Those of carbon are 98.9, 1.1. All right, so other elements that we are going to talk about, in particular in this lecture, are sulfur, chlorine, and bromine. These are common elements that also get to be bound to carbon in many organic molecules. And the thing to notice right here is that from the point of view of sulfur, it's really all about sulfur 32 and sulfur 34, which we have a value of 4% roughly speaking for sulfur 34. Sulfur 33 is actually pretty small, less than 1%, so it's not all that important in the parameters we're going to be looking at. But the thing to notice right here is that sulfur 32 and sulfur 34 are going to be the predominant things we're going to be looking at, and there is a difference of 2 atomic masses between those two isotopes. Similarly, chlorine 35 and chlorine 37 are the two natural isotopes of chlorine. They are 2 isotopic masses away from each other, but the abundances are 76% and 24%. This means that you have 3 times as much chlorine 35 as you do chlorine 37. And for bromine, we have bromine 79 and bromine 81 as natural isotopes of bromine, which are roughly on a 50-50% bases found in elemental bromine. And so what this means is that you're going to have 1 part bromine 79, 1 part bromine 81 in any bromine sample. All right, and let's think about these values, right? So chlorine 35 is going to be 3 times as big as chlorine 37, and bromine 79 is going to be just as big as bromine 81. And once again, they are separated by an overall atomic mass difference of 2. All right, now the main elements that we're going to be focusing on are going to be the ones highlighted here in orange. So hydrogen, carbon, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, sulfur, and phosphorus. And we'll show you some of the rules that you have to be aware of in terms of determining your molecular formulas just by looking at the abundances of these elements in a batch of sample. All right, so with all this being said, um, in the next video, what I'm going to show you is the rules for determining how much carbon, how much nitrogen, chlorine, bromine, oxygen, and sulfur you may have in an actual mass spectrum for an unknown substance. And this will be the basis for actually getting molecular formulas. So I will see you in the next video.